Ladies and gentlemen, welcome to lecture 15.1 in the Math 4000, problem solving for Putnam. I would like to, since I've been absent for quite some time right now, I would like to continue with integration. And in fact, today we will talk about the mean value theorems for integrals. In fact, I'll discuss the two mean value theorems for integrals, the first and the second one. And then we will see some applications of these two. We'll see various problems given at previous Putnam exams or other contests and Olympiads and so on. All right, so let's get started. So first, I would like to start with the statement of the two theorems, and then we'll see some applications. So so let's start with the first mean value theorem for integrals. So the first, mean value theorem for integrals. Basically, this is just a version of the classical mean value theorem, but this time instead of stating it for differentiable functions, it will be applied for the antiderivative, and it has the following statement. So we consider f. So let f be defined on a closed interval a b. Be a continuous function such that, then there is some c in AB such that the following holds true, such that, and let me write this, the integral from a to b of f of x dx is b minus a times f of c. So that's the statement of the first mean value theorem for integrals. Right? Okay. Right, as you can see, this is nothing else, just an application of the classical mean value theorem, but for the antiderivative, right? On the interval AB. Anyway, I'm not going to go into the proof of this. This is done usually in even in a Calc 1 course, but the proof is covered more in an advanced calculus course. All right, so that's the first mean value theorem for integrals. And now let's see the second one. So the second mean value theorem for integrals. So that's the first one. And now the second mean value theorem for integrals. This time, we will deal with two functions. So let's consider, let's say, let f and g be two functions defined real values functions defined on the interval AB. So two, or let's say continuous functions. Such that g has a constant sign on the interval AB. So such that g of x is different than 0 for all x in AB. Okay, then there is some c in AB such that the following holds, such that the integral from a to b of f of x times g of x dx is f of c times the integral from a to b of g of x dx. So that's the statement of the second mean value theorem, right? Let's look at this. You see the difference between these two is that, well, the obvious difference is that the first one involves only one function, right, f, and while the second one involves two functions, f and g. And we have this condition here that g has a constant sign. This is important. Anyway, usually the second mean value theorem in any classical textbook in introduction and analysis, it's proven by using the intermediate value property of the functions f and g. But also there is also a proof which is more of a differential flavor involving Rolle's theorem. But like I said, I'm not going to go into details since this is not the purpose of our lecture today. Okay, so these are the two theorems that I wanted to talk about. In fact, I would like to point out a remark here. And the remark that I want to point out is that these, if you look at these two theorems, right, you can, the second mean value theorem implies the first mean value theorem. If you look closely, only if we take G to be so, let's point out this remark. If, let's say, a G is a constant function, right? Let's say constant function 1, right? Then we recover the first mean value theorem. Okay, right? It's quite obvious that we obtain the first mean value theorem. All right, great. Now let's see some applications. And so now let's see some applications. And the first application that I have in mind, we will see several applications of these two theorems. Usually, when I usually teach this in a Calculus 1 course, I don't dwell too much on applications because most of them are tricky and there is no point in a Calculus 1 course. But in an advanced calculus course, it's more feasible for me to cover some applications. But anyway, let's see some application. And the first one that I have in mind is the following. And this was a problem, which is a very old problem. It was, in fact, it's a very famous problem, but let me state it first. If A0, A1, A2, AN, so if I have these are real numbers, satisfying this condition, and I'm going to write it in this way, so the sum all ai's over I plus 1 from I from 0 to n, so this sum is 0. So if we have these numbers satisfying this condition, show that the equation, so the polynomial equation, basically the equation, let's write it an x to the power n plus an minus 1 x to the power n minus x minus 1 plus a1x plus a0 equals 0. So this equation has at least one real root. So that's the first problem that I have in mind. And this was, like I said, it was a Putnam problem in 1958. So a Putnam A1, let's say, 1958. But I would like to also make a comment here. Also, this problem was given in a the so-called Cambridge mathematical tripos. So these are the exams in the old exams in the Cambridge University, and one of Hardy's favorite exam problems from 1929, in fact. But also, like I said, this was also a Putnam A1 in 1958. Well, I've done this problem in the lecture, I think, 14, if I remember correctly, where we actually use Rawls' theorem. And then I told you at that point that there is actually a simpler solution by just using the mean value theorem. So let's see. So if we have the mean value theorem in mind, the solution will be quite easy. So in fact, we will have to look for this guy here. Look at this guy here. And maybe we can reinterpret this in a certain way. Maybe we can rewrite this in a certain way to be more exact. All right. So maybe this term here, if we look at this guy, maybe this comes from some kind of an integral. So first, let's observe something. So observe that this guy here, 1 over I plus 1, if you look at this, is nothing else than just the integral from 0 to 1 of x to the power I dx, right? So the antiderivative is, right, is x to the power I over I plus 1 from 0 to 1, which is nothing else than 1 over I plus 1. Great. And our condition can be rewritten as, so let's write it in this way. So 0 is the sum from 0 to n of ai over I plus 1. So this guy here, if you look, so we can write this in this way. So it's the sum from 0 to n of ai times the integral from 0 to 1 of x to the power I dx. Or if you want, we know that this is a finite sum, so it will commute with the integral since the integral is additive. So this would be nothing else than just the sum from 0 to n of, the integral from 0 to 1. Okay, let me rewrite it. So this is the integral from 0 to 1 of the sum from I equals 0 to n of ai x to the power I dx. So we know that this guy is 0. All right. So let's call this guy here p of x. So we know that the integral of from 0 to 1 of p of x dx is 0. So now we're in a good position to apply the first mean value theorem. So by the first mean value theorem. So from now on, I think I will abbreviate for integrals. I will abbreviate this so that I wouldn't write. So I will abbreviate this as MVT. So first MVT for integrals. So let me write it in this way. There is some C in 0, 1 such that we have the following, or let me say x0 so x naught in 0, 1 such that we have that the integral from 0 to 1 of p of x dx is nothing else than just, well, 1 minus 1 times p of x naught. But this guy is 0, and this guy is nothing else than just the p of x naught, which is exactly what we wanted to prove, right? We wanted to show that, we see here, that our equation, right, this equation here, has at least one real root, which is exactly what we want. So this ends the problem. You see, you can do this in a fairly easier way by just observing this fact here. So that was the only thing you needed to observe. And then from here, it's quite clear. The only thing you have to use is just the mean value theorem for integrals, the first mean value theorem for integrals. All right, that's great. I also suggest you go back to lecture 14, I think, and where I do the same problem, but I solve the same problem using Rolle's theorem. In any case, they're equivalent. Essentially, they're equivalent. Okay, now let me show you another problem. Oh, and I'll show you multiple solutions to this next problem. The second problem says the following. It says that let f of x be a differentiable function defined on the closed interval AB. So I'm just going to state it the way it was stated in the Putnam exam. On the closed interval 0, 1, sorry, such that the derivative of f in absolute value is less or equal than a constant m for all x in 0, 1. Okay. Prove that we have the following. So the integral, so I'm going to take the absolute value. So I'm going to take the integral of f of x dx. And I'm going to subtract here, it's a Riemann sum. So, and I would like to estimate this. So we know that the Riemann sum, right, this sum here, converges as n approaches infinity to the integral from 0 to 1 of f of x dx. But this will be less or equal than m over n. And in fact here, this I would like to say up right from the start that this bound is quite weak. We will see that we can replace this by m over 2n, but this is how it was stated in the Putnam. So this was a Putnam, I think it was 1947. All right, and now I'll show you the first solution is the official solution. So solution 1. All right. So the official solution is the following. So let's denote, so let's consider EK to be this guy, the integral from k minus 1 over n, from 0 to, from k minus 1 over n to k over n of f of x dx minus 1 over n f of k over n. So we're going to have this. And for k from 1 to and n, all the way to n. So I'm going to consider this number. And now what I'm going to do, the idea is to apply the classical mean value, the mean value theorems for integrals, and then also to combine this with another application of the classical mean value theorem for differentiable functions. And in fact, I would like to stay here that this is why the inequality will become weaker, because once we apply the mean value theorems twice, you'll make things weaker than they should be. So clearly, since f is differentiable, right? Since f is differentiable, it follows that well, f is continuous, right? And therefore, by the mean value, the first mean value theorems for integrals, by the first mean value theorem for integrals, there exists a number, say, right, eta k from in this interval k minus 1 over n, k over n, and such that, and we have that the integral from k minus 1 over n to k over n of f of x dx, this guy will be 1 over n times f of nu k, right? Okay. F of eta k, right? But on the other hand, so let's keep this relation in mind. So let's denote this by 1. But on the other hand, by the classical mean value theorem, so by the mean value theorem, right, for derivatives, okay, let me write it like this. Right, there exists a number this time, let's say ck, right, and this ck will be with eta k is ck less than ck less than k over n, and we will have the following relation. So let's write it in this way. So f of eta k minus f of k over n will be eta k minus k over n times f prime of ck. Okay, so that will be, let's say, the second relation. All right, so we have these two. So let's look at them. And now we can look and we can estimate. Let's not forget that we would like to estimate this guy here, right? This is the guy we would like to estimate, because this will be important when we will try to estimate, when we will sum this all these AKs, we will obtain exactly our estimate, the quantity that we would like to estimate here, right? In our problem. All right, so let's see here. So now we have let's see, what do we have? So let's look closely. So we have the following. So let's see, we have the absolute value of AK. This will be, so let's see, so it's one, is this integral minus 1 over, so this would be 1 over n times, let's look around. So this would be minus 1 over n kn. Okay. So this would be the absolute value of f of eta k minus f of k over n, right? And this would be nothing else than, since we know who this is, so this would be 1 over n times the absolute value of so we know for that. So this would be eta k minus k over n, right, times f prime of ck. Well, I hope I didn't do any mistakes here. Let me just check. So okay, all right, so we have this, and now we can estimate now this, guys, right? And here we can look, and this will be, if we less than 1 over n squared times, so this is less than 1 over n times 1 times m. And now guess what? Once we add all these together, right? So finally, we obtain the following. Now it's quite clear what will happen. So now we have that this quantity that we would like to estimate. So the integral of f minus 1 over n times the sum of k over n. So this quantity here in absolute value will be less or equal than, in fact, let me write it in so that we can see who this is. So this is nothing else than just the sum from k equals 1 to n of ek. And this guy, if we sum up all these ak's, will be nothing else than just n times m over n squared, which will give us m over n. And that's the first solution. As you can see, it's not quite productive since I applied twice. Well, I applied the mean value theorem once for the integrals and then for differentiable functions. But now let me show you a more direct solution. So this was the official solution. And like I said, and let me, this one here, this constant here can be improved. So let me mention this can be improved. And this can be improved to m over 2n. And now let me just give you the second solution. So the second solution, solution number 2, again, we will use the mean value theorem for derivatives. And this time we'll do it in a sleek way, but it's much more direct. So we have the following. So let's write that difference. So we have that the absolute value of f minus this sum, 1 over n times the sum of f of k over n, right, in absolute value. And this guy, we will break this integrals into this integrals, right, so we will write it in this way. So this will be the sum from, in fact, let me write it like this. So from 0 to k to n minus 1 of the integral from k over n to k plus 1 over n. Either way, I could have started from 1, but it doesn't really matter that much. F of k over n minus f of x. So I'm going to write it in this way. And I know at this point, once I observe this, so by applying the triangle inequality, this will be less or equal than the sum from k equals 0 to n minus 1, sorry, of the integral from k over n to k plus 1 over n. And now I'm going to put the absolute value inside here. So this will be f of k over n minus f of x dx. So here, let me just mention, we apply this inequality. The absolute value of f is less or equal than the integral of the absolute value of f. So this is what we applied here. All right. Great. And now what we would like to do is maybe we can control this guy in some way. And now we are in a good position to apply the mean value theorem. So let's do it. So by the mean value theorem for derivatives, right? So by the mean value theorem for derivatives for all, let's say k, in this set, 0, 1, all the way to n minus 1, and for any x, and this interval, k over n, k plus 1 over n, right? There exists, let's say, a ck in this interval k over n x, right? Such that the absolute value of f of x minus f of k over n right, is x minus k over n times the absolute value of f prime of ck. And now we know that the derivative is less than m, so we know this here, right? So this guy is less or equal than m, we know that. So this implies that this guy here is less or equal than x minus k over n times m. Okay, great. So finally, this will give us that the integral from 0 to 1 of f of x dx minus this sum, let's say 1 over n times the from k equals 0 to n minus 1 of f of k over n. So this guy here, right? And now we'd like to estimate this. This will be less or equal than this constant m times, and now we'll have the sum of this. So it will be the sum from k equals 0 to n minus 1 of, and now let's be careful, the integral from k over n to k over n plus 1, k plus 1 over n. And now we will have here x minus k over n dx. And now I will leave it to you as an exercise. So this guy here, if you look, if you evaluate this integral, this will be, well, what will be 1 over, well, you will have to sum. It will be everything. If you evaluate, it will be just m over 2n, which is exactly, well, it's better than what we wanted to prove. You see? So the main trick here was just to rewrite this. So to break this integral, so basically the trick here was, let me just mention this. So here the trick was to break this integral f of x, the integral from 0 to 1 of f of x, as we can break it in this way. So we can break this as the sum of k equals 0 to n minus 1 of these integrals from k over n to k plus 1 over n of f of x dx. So that was the secret. And once you have this in mind, then everything will just follow more or less, right? So as you can see, I would say this is a much more straightforward solution than the official one. It's much more efficient. I don't need to apply the mean value theorems twice or whatever. I don't need to combine the mean value theorem for integrals with the mean value with the classical mean value theorem. But I wanted you to show you the first solution because I used it's an application of the first mean value theorem for integrals. So I wanted to show you that. All right. But now let's see another solution. We can actually go even further. Solution 3. We would like to use Taylor's expansion theorem. So, like I said, we will prove the same bound, m over 2n, but this time we use Taylor series. So this will be based on Taylor series. All right, so let's do it. So let me denote, let f of x be the antiderivative, so the integral from 0 to x of f of t dt, right? And well, we would like to expand this by Taylor's theorem. So around the point k over n. So expand in Taylor series. On the interval. So we will see on this interval k minus 1 over n, k over n, around the point, let's say x0, this will be k over n. And we will apply this for the antiderivative. So, right, so that's what we're going to do. So let's see, what do we have? So we have the following. So we have that f of k minus 1 over n, And now let's be careful here. So this will be f of k over n plus negative 1 over n, right, times f prime of k over n, right, because it's k minus 1 over n minus k over n, which is negative 1 over n, right, times the derivative. And now plus, you will have your negative 1 over n squared times f second prime of theta k, let's say. I'm going to change the notation. I could have used the same notation with psi, but I can change it to theta. So where theta is a number between, it's in this interval, k minus 1 over n, k over n. All right, great. So we have this relation. And now let's rewrite this. Let's rewrite this fellow here. So since we know that f prime of f is f, let's call this star becomes the following. So let's see. So we will have what? So let's see, what do we have? And in fact, let me just use the same notation, right? So k, right? Let's see. Okay, let's rewrite it. So f of k minus 1 over n minus f of k over n minus 1 over n times f of k over n plus 1 over 2n squared f prime over ck for some delta k, for delta k in the interval k minus 1 over n, k over n. All right, great. This guy here this is equal here. Or if we use the same notation, so using the previous the notation from solution 1, so that I don't need to write again, and for ek, and let me remind you that the notation for ek was the following. So let me go back. What was it? So is this integral? So the integral from k minus 1 over n, okay? Of f of x dx minus 1 over n f of kn. So once we use this notation, as you can see here, and let me point out this right here, this thing here, if we look at the difference, so f of k over n minus f of k minus 1 over n, right, by the fundamental theorem of calculus, this is the integral from k minus 1 over n to k over n of f of x dx. So keep in mind this. So this is by the fundamental theorem of calculus. All right, so using this notation, we can rewrite star as in the following. So we can rewrite as ek is nothing else than just yes, is nothing else than just negative 1 over 2n squared times f prime of theta k for some theta k in this interval. All right, great. And now the only thing we need to do is just to take the absolute value to sum up, and then there we go. Finally, we obtain that okay, let's do it like this. So the absolute value of the integral right? This will be nothing else than the absolute value, the sum of a k, which will be less or equal than the sum of the absolute value of each ak. All right. And this guy, since we know that each ak is this guy here, right, is -1/2n squared times this, so it's this right here, right? Since we have this, this will imply, and we know that the first derivative of f in absolute value is less or equal than m, then we can say that this is less or equal than, and well, again, it will give you that this is nothing else m/2n. Anyway, and that's the final, so that's the third solution for this problem. As you can see, there are plenty of solutions for problems, for this problem, 3 solutions. I think all 3 of them are beautiful, but like I said, the first one is not quite productive because it doesn't give you sharp bound. Okay. All right, so let's get back to, so now let me do another problem. So problem 3. And the problem says the following. So prove that if a function f is continuous on the closed interval at 0 pi, and if the integral from 0 to pi of f of theta cosine of theta d theta is the same as the integral from 0 to pi of f of theta times sine of theta d theta, and moreover these two are equal to 0, right? Then there exists points, let's say alpha and beta, such that 0 is less than alpha, less than beta, less than pi, and we have that f of alpha is the same as f of beta, and both of them are equal to 0. Well, this was a Putnam, it was a difficult Putnam problem. So this was a Putnam A5, well, some time ago, long time ago, let's say 1963. That's the statement. Well, as you can look at the statement, it basically it kind of tells you like maybe there is some kind of a mean value, an application of the mean value theorem for integrals. Right. So let's see. So let's look at this. Well, let's assume, so we may assume that f is not 0, right? So let's assume this. And then since the integral from 0 to pi of, since we know that the integral, the second integral, if you look at it, right? If you look at this guy here, if you look at this integral here, right? So from this one, so from the integral from 0 to pi of f of theta sine of theta d theta, since we know that this is 0, and we also know that the sine of theta is positive, right, for theta between 0 and pi. Since this happens, right, then f, then since f must change its sign somewhere on the interval on 0 pi, right? It must happen this. And let's just say at alpha. So let's just say that this f will change sign at alpha. And now let's analyze this. If alpha is the only 0 of f on 0 pi, right? Then f changes one sign on 0 alpha. Then f changes one sign on the interval 0 alpha, right? Okay. And the opposites and the opposite sign, yes, and the opposite sign on alpha pi. Okay, that's great. Well, in any case, so we will have that the integral from 0 to pi of f of theta times sine of theta minus alpha, right, d theta, is different than 0. So this will happen, right? All right, great. But on the other hand, I would like to look at this integral and I would like to expand it. So I'd like to look at this guy here and I'd like to expand it. So, but this integral, if we look closely, if we have a closer look at this integral, we have that the integral from 0 to pi of f of theta times sine of theta minus alpha d theta. So this guy here is nothing else. If we expand this guy, right? So we will have, let's see, what do we have? So we have a cosine alpha times the integral. So let me just write it directly. So it's a cosine alpha times the integral from 0 to pi of f of theta sine of theta d theta minus sine of alpha times the integral from 0 to pi of f of theta cosine of theta d theta. And these guys, if you look at them, we know that this guy is 0, this guy is 0, so everything will be 0, which is a contradiction if you look at it. So contradiction. Well, therefore this implies that, so this implies that there exists a beta, let's say beta in this interval alpha pi such that f of beta is 0. F of beta is 0. And that's the end of the problem. We see it was quite easy. This was a very easy problem, I would say. And now let me do a very, very similar one. Again, it was a Putnam A5, but this time I think it was 1980. So let me, application 4. And the problem says the following. So this time we will have this problem will involve a polynomial, but the relation, the integral relations will be just the same. So let P of t be a non-constant polynomial with real coefficients, right? And now we would like to prove that the system, so prove that the system of simultaneous equations, and let me write it in this way: 0 is the integral from 0 to x of p of t sine of t dt is the integral from 0 to x of p of t times cosine of t dt, right? So this system of simultaneous has only finitely many solutions. All right. And this was a Putnam 85 in 1980. Right, as you can see, it's somewhat similar to the previous problem. Right. So this is a little bit more, it's a bit trickier than the previous one, because when you look at this system of equations, right, the two equations, the first integral is 0 and the second integral equals 0, right? If you look at these, this system, the good part is that we're dealing with a polynomial, so we can integrate that repeatedly. So maybe that would be maybe a good idea to try. Maybe we should do repeated integration by parts, and because at some point it will just stop, right? And maybe we can combine these two equations in such a way that we will obtain some relationship between the derivatives of polynomials or whatever. All right, let's see. So the thing is that the main idea is to consider this very tricky thing. So we consider the polynomial. And let me show you how so Q, and I'm going to write it in this way. So it's going to be P, and I'm going to take minus the second derivative plus the fourth derivative, right, of P, minus and so on. So I'll alternate the signs in some way. And now using repeated integration by parts. Anyway, I'm not going to go into details. Integration by parts. I'm sure you can do the computations by yourself. We have, and let me show you how funny this would look. So we have that the integral from 0 to x of p of t times sine of t dt. And now pay attention, since I'm using this notation, I'm just integrating over and over again with sine, cosine, as we take the derivative, right? Then this will be at some point, and I'll just leave it to you to check this as an exercise. This will be something like this. So it will be negative q of x times cosine of x plus q prime of x times sine of x, right? Plus q of 0. And we know that this guy is 0. Great. But also, we can do the same thing for the second integral. So we know that the second integral is the integral from 0 to x of p of t times cosine of t dt. So this will be, and now this time we will have something like this. It will be q of x times sine of x plus q prime of x times cosine of x minus q prime of 0. And this will be 0. So therefore, we have these two equations here. And if you look at these two equations, this and this one, right? Just these two equations. So if you combine these two, right, I think we can, at this point, we can write q of x from these two equations. So this implies that so let's see. So we want to write q of x. So it's q of x minus. So let's see. Okay, so this will give us, so let's write it, q of x is, and I hope I'm not doing a mistake in computation, so this will be sine, cosine. Okay. So this would be q prime of 0 times the sine of x plus q of 0 times cosine of x. Yeah. So we multiply the first one by cosine and the second one by sine, and we can add them up, and right. So we'll get this relation. Okay, so we also have this one, and this relation will turn out to be crucial because, you know, at this point, let's do the following observations. So since P and Q are polynomials of positive degree, and let's call this equation, let's call this E. We denote this by E. So since P and Q are polynomials, of positive degree, and the right side of the equation E, so the right hand side of E, right, so is bounded. So this guy here, if you look at this guy here, this is bounded. So this guy, right? Since the right hand side of E is bounded, right? Then we can say that the equation E, then the equation E, right? So what can we say? We say that the equation E has all of its solutions in some interval, let's say. And this will be some interval of, let's say, for values x less than or equal than m. In some interval, let's say negative mm, it doesn't matter. Well, the problem is that, well, in such an interval, these functions, so p of x times sine of x, right, has only finitely many zeros, has only finitely many zeros. Right? And since and this function, right, the integral from 0 to x of pi, p of t times sine of t dt. So this equation has at most one more zero by Rolle's theorem, right? Has at most one more zero by Rolle's theorem, and we're done, right? And why do I say by Rolle's theorem? Well, or by the mean value theorem if you want, it doesn't matter. So this is just, and that's it. That's the end of the problem, right? Because we proved that this system of equations of the system formed by these two equations has only finitely many solutions. All right, beautiful. Now in the remaining time, like I said, I would like to do as many problems as possible to capture more techniques using mean value mean value theorems techniques. I would like to do two more problems. So the fifth problem, it's a pretty classical problem, but I would like to do it because I've done this a couple of times for differentiable functions, but I would like to show you the same technique, how it works when there are integrals involved. And the problem says the following. So let me consider, let f defined on 0, 1 and real valued be a continuous function. Such that the integral from 0 to 1 of f is 0. And now we would like to show that there exists number c in 0, 1 such that f of c is the integral from 0 to c of f of x dx. So that's the problem. Anyway, it's pretty classical at this point. And well, if you look, I think we have done a similar problem when we were, remember there was this Putnam problem where we wanted to show, well, I think there was this function that had at least 5 zeros, and then we wanted to show that some kind of a linear combination of the derivatives all the way up to the third derivative has at least 2 zeros. And you know, we wanted to use Rolle's theorem repeatedly for the function, for the first derivative, for the second derivative, and all the way to the third derivative. But there is also one thing that that stood up there, and what is stood up is that the way we constructed the function. And the way we constructed the function is that, remember, when we have this, let's look at this guy. When you look at this guy here, you see you have something like f equals f prime, right, for the antiderivative. So it looks more like, well, I don't want to get into this because this will be the last chapter for this when we talk about the differential equations, and you will see some kind of techniques. But also this is like a first order ODE, whatever that means. So this is a first order ODE. And well, usually when you solve this ODE, there is e to the power x involved there. So maybe we should construct a function, an auxiliary function, which looks a little bit like this. So consider the function, the auxiliary vector function. Let's say phi, and define on the interval 0, 1 real valued, and phi of t is e to the negative t times the integral from 0 to t of f of x dx. So we have this function, right? As you can see, it's pretty, the function looks nice. You see that you have that e to the negative t there, that integrand factor, if you want to call it like this. And clearly this is a differentiable function. So clearly phi is a differentiable function. And moreover, its derivative, and the derivative is given by phi prime of t is, well, so it's negative e to the negative t times the integral of f plus e to the negative t times f of t, which basically this is nothing else than just e to the negative t times f of t minus the integral from 0 to t of f of x dx. All right, great. All right, and now let's look at this function. Well, we have this condition here that we did not explore yet. So this condition here, and we would like to see how we can translate, how does that condition will translate in terms of our new function phi. Well, let's look at the endpoints. So observe that phi of 0 is clearly 0, and phi of 1, if you look, is nothing else than just 1 over e times the integral from 0 to 1 of f of x dx. And this guy, since we know from the hypothesis that this is 0, this will be 0. So, and at this point, we're in a great position to apply Rolle's theorem. So by Rolle's theorem, there is a point, let's say C in 0, 1, such that phi prime of C is 0, or equivalently, this is nothing else than just f of C, or e to the negative c, f of C minus the integral from 0 to c of f of x dx is 0. And clearly the conclusion follows. And the conclusion follows. And that's it. So this was the problem. So it's a pretty classical problem. It's a very nice problem. And the main idea, the main trick, if you want to put it this way, is just to consider this auxiliary function, this one here. That was the trick. And of course, you can play around with these kind of functions, and you can construct plenty of them. Like it depends, depending on the situation. Okay. Now I would like to draw your attention with one more problem, and after this, I'm going to stop. And well, I'm not going to stop with the integrals because there's a lot of things to cover here. But I will stop with the applications of the mean value theorems for integrals. But also I'd like to do this problem. It's a very nice problem. It's a beauty. This problem says the following. So it says that let f, defined on a closed interval 0, 1, real value, be a continuous function such that the integral from 0 to 1, again, we have the same condition of f of x dx is 0. Then show that there exists a number c in 0, 1 such that the integral from 0 to c of x f of x dx is 0. Okay, so that's the statement. I think this was a Romanian National Math Olympiad, I think, in 2006. I do remember precisely the year of this problem. And well, at first the problem maybe doesn't tell you much, but it has a deeper meaning that it actually seems. In fact, I'll just make a small comment here, is that you can replace that x with any function, let's say phi or whatever function that has a certain properties. And then you can view this integral as the Volterra operator. So basically it tells you that the Volterra operator has a 0 in some function space. All right, but this is the simplest case, let's say. And the problem is, I would say it's tricky. It's so we will argue by contradiction. So assume by contradiction that the integral from 0 to t of x f of x dx is different than 0 for all t in 0, 1, right? So let's assume this. And well, without loss of generality, we can assume that we may assume that the integral is actually positive, right? Okay. And now let's consider, so let me consider the antiderivative f of t to be the integral from 0 to t of f of x dx. And now the idea is we would like to relate these two integrals, right? So we would like to relate this integral from 0 to t of x f of x dx, right? So we would like to relate these two integrals. So this one here and with this one here. So that is the main idea. So how can we do this? Well, we can integrate by parts. So integrating by parts, we have that. So let's see, what do we have? So we have that this integral. So let me put it this way: 0 is less than this integral from 0 to t of f of x dx. And this guy here, we can so we can write this as the integral from 0 to t of x of f prime of x, right, dx. And this would be nothing else than just t f of t minus the integral from 0 to t of f of x dx, right? So the integral of the antiderivative. Great. So now let's take by passing to the limit, as t approaches 1, we obtain that. Let's see, what do we obtain? So we obtain the following. So we obtain that f of 1, which is 0. So we will get that that the integral from 0 to 1 of f of x dx is less or equal than 0. So let's call this star. So we will get this relation. I hope it's quite clear why do we get this, right? Since we pass to the limit, the inequality being strict, but as we take the limit, the inequality can also be it's less or equal than 0, right? Okay, so we have this relation. So maybe now we can cook something which will give me the opposite inequality. And in this way, I'll get a contradiction. So now we consider the following function. So consider the differentiable function and let's call this h, capital H from 0 to 1 and real value. And this is given by, so it will be a piecewise function. It's h of t is the integral from 0 to t of f of x dx over t if t is different than 0 and 0 if t is 0. All right, so this is the piecewise function. Well, it's clearly differentiable, so I don't have any problems. It's continuous, whatever. And moreover, it is easy to see that the derivative h prime of t, the derivative of this guy, right, by just applying the quotient rule, is nothing else than, what is it? So it's a t times f of t minus the integral from 0 to t of f of x dx, everything over t squared. And what do we know about this? So we know that this guy, so what do we know? Okay, we know that from this one here, right? You see this relation. So look at this guy here, right? Tf of t. This is greater than 0. So this guy here, we know that it's greater than 0. So this is greater than 0. That's great. And now, since this is greater than 0, this implies that h is increasing. Okay, which means that increasing on the interval 0, 1. And now since h of 0 is 0, right? So this guy is 0. It follows that h of 1 is greater than h of 0. So it's greater than 0. Or equivalently, if we write h of 1, or equivalently, let's see who h of 1 is. Well, you just plug it in into this function here. So it will be that, it will imply that the integral from 0 to 1 of f of t dt, sorry, f of x dx, anyway, it doesn't matter. This will be greater than 0. Beautiful. So let's call this star star. But let's look around. Look at the two relations. At one hand, the integral of capital f is less than 0. On the other hand, is greater than 0. So this is a contradiction. Very beautiful problem and solution. And we're done. Where did the contradiction come from? Well, let's look back. It comes from my assumption here. You see? That I assume that this is different than 0. So therefore, let me just write it. So therefore, there exists a C in 0, 1 such that the integral from 0 to C of x, f of x dx is 0, and we're done. Right? So that was the problem. It's a very beautiful problem, very difficult, I would say. I think it was one of the, if not the most difficult problem at the National Math Olympiad for high school seniors in Romania. All right. Okay, I think I'm gonna stop here. So this will conclude the second part of lecture 15. So this will be this was lecture 15.1. Well, the next lecture will be devoted to integral inequalities, and you'll see there as well a bunch of techniques. And then afterwards, I will show you how we can correlate integrals with infinite sums and so on, how to pass the limit inside the integral and so on. All right, I'll stop here. Thank you very much.